goes on, it shouldn't lower the credibility of it.
Disclaimer.
Disclaimer. Yeah. Right. So yeah. So actually, Umang asked me to give a little talk on some exciting things in physics. So I thought that I'll try to tell you some fun concepts. It's a very vast field, so I don't think we can do much in 1 hour. Here you can also say, listen. So anyway, so let's start, okay? So all of you, yeah, so most of us, are you from engineering backgrounds or what are your backgrounds?
Engineering.
What about you?
Optometry, vision science.
Vision science, okay. Alright, so some of you are from engineering and some of you are from vision science.
That's pretty accurate. Yeah.
Okay, so, but no matter what, all of us know what happens if we put one electron next to another electron, or like the north pole of a magnet and the north pole of another magnet, right? So there is a repulsive force. So we know that if we try to take two magnets and put the north poles together, there is a repulsive force. Similarly,
I can do it though. Once you get past the magnetic force, they stick.
yeah, if you try hard enough, right?
Yeah, and I can do that.
So same thing happens, like charges repel, so two charges which are negative also repel. So now the question that scientists would ask is, how does this happen? Like supposing an electron is here and another electron is here, like how does this know that it has to repel? So you can think of this as an actionated distance. So because there is a distance and you know that things take time to communicate, but yet this seems to be rippling, then you might think that there is an actionated distance going on, right? So originally, when you think about Newton's laws, you basically supposing I say this repels because this is at a distance r and it has a repulsive force E squared divided by r, where E is some number, then yes, so I have given you exactly the force with which it repels. But I have not told you how this rippling is happening. It's like it's at some distance r and it's feeling the force and it's rippling, right? It's an actionated distance kind of thing. So what people proposed was that this electron actually creates an electric field around it. So or just like around a magnet you have a magnetic field, around an electron you have an electric field, and this electron feels.
And I won't touch an electron.
And this electron here feels that field, and then it repels. Now if you ask, okay, so there is a magnetic, so you now created this idea that there is a field around this electron and it feels the field and then it's rippling, right? So you have that idea. Now if you now start changing the position of that electron, the field changes, right? And this electron also feels different forces. Now how fast is this field change being communicated between the two electrons? You will find that it happens at the speed of light, right? So the magnetic field, electromagnetic field around an electron is propagating at the speed of light. So then, in the evolution of physics, then people started thinking light as a particle and as a wave. So it's called a photon. So eventually it was postulated that photon is actually, or light particle is carrier of the electromagnetic field. So now the view can be something like this, of why an electron feels a force, and this is the kind of where you can, so you can see that an electron comes in, it emits light, which another electron absorbs. So when it emits something, then you, if supposing you throw a bucket of water, you will get a kick, right? If you are on skates and you throw something, then you will get a kick because of energy momentum conservation, right? So you get a kick back because you threw an electron. Another electron captures it and then it captures the momentum and it gets a kick. And that feels like a repulsive force. So the idea that there was action at a distance got replaced by the idea that there is a field which changed, which then got replaced with the idea that that field is actually a quantum field. That field comes in quanta that we call photons, and actually these photons are exchanged. And that explains the electromagnetic force. So that is the kind of picture that we have. So particle physics is, or this kind of physics is about particles like electrons and the forces with which they interact with each other, right? And now we will see how this idea gets. Yeah, you have a question?
Yeah, but that still doesn't explain why they both actually repel, right? Because that action, or whatever the distance that you said, like could hold true even for like opposites attract, right? I mean, so
Right.
within
So why do opposite charges
Attract,
attract?
yeah.
While so now that's I didn't want to get into that.
Oh, okay.
But no, but that's a deeper question that requires a little bit of quantum mechanics also to understand. Now what happens is, now let's assume that this photon was emitted by this electron in this direction instead of that direction, right? So it will get a kick towards, and let's assume that this was a positively charged particle. So instead of, supposing it kicked the photon this way, then it will get kicked this way, right? If you throw something like this, you get a rebound this way, right? But if you threw the photon this way, then you will go towards the other particle. Now, but then this photon is traveling this way, and you will feel that that electron or that positive particle won't catch that photon, because if it did catch that photon, then it would also get a kick in this way, and it will look like an attraction. So what happens is that in quantum mechanics, what happens is that position and momentum cannot be simultaneously measured. You must have heard of the uncertainty principle. How many of you have heard of this?
I've heard but never understood that.
So yeah, I didn't particularly want to get into that, but roughly what it says is that there is a limit to the accuracy with, like, a measurement disturbs the system. So if supposing you wanted to measure the location of something, what you would use are so you would typically use a ruler, right, to measure a position. So now if you think of light as a wave, it has a wavelength, and you can think of using this wavelength as a measure, to measure the distance as a ruler. So to more accurately measure something, you will use a wavelength which is really small, like a ruler with very small divisions, to locate it correctly, right? Like you can't use a meter ruler and measure in centimeters, right? You'll use a millimeter ruler. But when you increase, for example, if you decrease the wavelength of light, that light has more energy, because the energy of a shorter wavelength light has greater energy. So you will necessarily use a highly energetic particle to measure the location of that very precisely. So when this highly energetic particle collides with this, while making the measurement, it disturbs it.
Okay.
So the more accurately you want to measure, the more is the disturbance. So you can't simultaneously measure the velocity or the momentum and the position. And that's what the uncertainty principle is about. So basically in the early 90s, essentially physicists found that when you're looking at really small systems, then our idea that, like, if you throw a ball, you can see its exact trajectory, as well as you can exactly measure the speed with which it's going. So this idea of, like, the big world does not apply to the small world, because locating things exactly are disturbing them, right? But the thing didn't end with it being a measurement problem. So then it was postulated that this is intrinsically the nature of the system, that actually not only can't be measured, but actually actually the system is such that it's uncertain, is intrinsically uncertain.
But Einstein didn't agree with that, right? Initially, at least.
Yeah, Einstein didn't agree with that, but experiments agree with that.
Okay.
So Einstein would have probably had to change his views on that.
Right.
Right. So now, this is why, for example, this, if supposing I have an electron and a photon being emitted this